and possibly even more. I'm looking at a very specific kind of radiation coming from hydrogen and other galaxies that just happen to be hosting active galactic nuclei in their center, and that tells me a lot about the large-scale structures of these galaxies. And since everything that I'm going to talk about today comes from radiation from hydrogen, I figure the best place to start would be looking at one hydrogen atom and seeing what it can tell us. So if you pull a random hydrogen atom out of space, chances are it's going to be in a configuration where the spins of the proton and electron are parallel. Now, if you don't know what spin is, or you never want to hear anything about quantum mechanics again, which is completely understandable, the only things that I'm going to describe about spin is that it's an intrinsic property of the particles, it's related to their energies, and it can be represented as a vector that can either point up or down. And chances are, if you pull a hydrogen atom out of space, these spins are going to be aligned in a parallel configuration. If you sit and watch your pet hydrogen atom for a long time, you'll find that the electron has a tendency to flip its spin from parallel to anti-parallel. And when that happens, it ejects a photon, and that photon has a wavelength of 21 centimeters, about 8 inches, that big. If that's all you're doing, sitting and watching this hydrogen atom waiting for something interesting to happen, you're going to be very bored because this radiative process takes about 11 million years. So it's not very useful. But, like I said, we were talking about galaxies, so one important thing to keep in mind is that hydrogen atoms tend to be small and galaxies tend to be a little bit bigger. So the schematic that I always like to show to get everyone in the same kind of headspace as to what we're looking at, here is a picture of a nearby galaxy, NGC 5055, from DSS. This is what the galaxy looks like in the optical. On the same scale for the same galaxy, this is what it looks like in the ultraviolet. This is from the Galaxy Evolution Explorer, or GALEX. Notice that the ultraviolet does a much better job of outlining spiral arms because the new star formation is emitting a bunch of ultraviolet radiation. And for the same galaxy on the same scale, this is what the neutral hydrogen distribution looks like. It covers a lot more space. So it doesn't really matter that one hydrogen atom takes 11 million years to give us this radiation because there tends to be a lot of hydrogen atoms in galaxies, so it looks like this radiation is coming from everywhere with a very steady stream coming towards us. So the telescope that I use to detect all of this stuff is the Green Bank telescope over in West Virginia. Here's a time lapse of what it looks like. Dr. Geis mentioned the range of the biggest optical telescopes that we have is about 30 meters. I can speak from experience that radio astronomers are kind of crazy, so they just went and built a 100-meter diameter dish, which is how big that thing is. And this is where I lose a lot of people when I try to tell them the things that I do, because in the receiver up there for 21 centimeters is the L-band, and it's just a giant bucket with a lid on it, because the wavelengths are big enough to just pass right through the lid. And also you can tell that it's observing during the day, because these wavelengths don't really care about what the weather is doing, which is great for me because I'm nearing the end of a very long observing run, and the term sleep schedule really has no more meaning to me anymore. So, how do we detect extragalactic H1? So what do we see? We're putting it through a radio telescope. We're going to look at spectra of these things. And there's a couple of things that we already know about the objects that we're looking at that might affect the shape of the emission line spectrum. And so I want to go through that with you real quick. One of the things that we can assume is that the galaxy is rotating. Another thing that we can assume is that the neutral gas extends far beyond the optical radius. And the third is that, in general, we can assume that the distribution is in a flat, symmetric disk. And what this all adds up to is you're looking at an object that systemically is moving away from you at some velocity with the expansion of the universe. So the emission line that you get from this 21 centimeter radiation is already going to be redshifted given that velocity. And also you have a thing that covers a lot of space and is also rotating. So you have a very large gradient of motion going around just due to its rotation. So you're going to get a broadening of the emission line from the rotation. And so because one side of the galaxy is always coming at you, so it looks like it's moving away from you slightly slower, and then the opposite on this side, it's rotating this way, where one side is always going to be moving away from you slightly faster. The only other thing that we need to take into account is that the disk is inclined, which is also going to affect the shape of the emission line that we get. So a while ago, I wrote a code that was meant to simulate kind of what this looks like. And without further ado, let me introduce you to the emission line profile of neutral hydrogen. And this is what I have lovingly referred to as the Batman profile. So what this thing is going to do is on the left, it's going to show you what the disk is doing in 3 dimensions. So it's going to start at 0 degrees edge-on orientation, and it's going to rotate up to 90 degrees face-on. On the right, it's going to show you the 2-dimensional projected image of the disk onto the sky, so what we would see if we were observing it. And on the far right is the distribution of radial velocities, or what the emission line profile would look like given a rotating disk in space. And this assumes, again, a flat, symmetric ring distribution. So let me play this real quick. It auto-scales too, because I'm not that good of a coder. But notice as it gets to a face-on orientation, the ears go away and it turns into a Gaussian profile. And then as it rotates back down, you start seeing the ears again. And the more edge-on it gets, the more pronounced the ears become. And that's because you need to think about the radial velocity vectors of the disk as it's rotating. So if it's completely edge-on, all of the motion is either towards you or away from you. So over here, you're getting a large flux of gas moving at this velocity. All of this gas moving over here, if it's rotating like this, is in the transverse direction. So all you see is the systemic motion of the object moving away from you. And over here, you're starting to see all the gas that's moving at this velocity. So you get 2 really large spikes on the side of the profile. If you start inclining the disk away from you, the radial velocity vectors also start leaning away from you. So you're seeing less and less of the gas that's moving at those velocities. So the ears start to dwindle, and then as soon as it gets face on, all of the motion is in the transverse direction. So you don't see any of the gas that's moving at those speeds. So you get a Gaussian distribution that's centered at whatever the systemic velocity of the object is moving away from you. So I've been telling you that in general we can assume that the H1 distribution is flat and symmetric. But of course, if we look at real-life integrated H1 maps, it's not symmetric or even. It's not symmetric. It's really, really not. These are integrated H1 maps from the H1 Nearby Galaxy Survey, or THINGS. On the left and on the right is their optical counterparts. So given all this, we can still make all the assumptions that we do about the motion of the disk, because even though neutral hydrogen kind of does what it wants and it is where it wants to be, it's still pretty spread out through the disk itself. So all of the analysis that we just did with all of the motion and the inclination of the galaxy itself all still applies. So what do these emission profiles look like in real life? Here's a galaxy that I recently observed. This is MCG 81111. Pretty well behaved Batman detection. But notice that the horns are a little asymmetric. The code that I showed you assumes that everything was symmetric. So if you see something in real life that doesn't match up, you can assume A, that the disk isn't flat, B, the disk isn't symmetric, C, both A and B, or D, a bunch of other things. But mainly it's those 2 things. So let's say that the distribution wasn't symmetric. Let's say that there was a lot of gas on this side of the galaxy and only a little bit on this side. You would get a larger flux of gas that's moving at this velocity compared to the amount of gas that you see moving at this velocity, and that would cause an asymmetry. Or let's say that there's a warp in the disk. So let's say this one is completely edge-on ear orientation, and there's a warp over here. So you would see more of the gas moving at this velocity than you would with the gas moving at this velocity. So again, you would get an asymmetry in the horns. And if you want to talk about asymmetries, then let me show you my favorite example. This is NGC 3227, who looks like he lost an ear. This is a galaxy that's interacting with its neighbor, NGC 3226, and you can bet that that's going to cause a dramatic change in the H1 distribution of both galaxies. Because what I always like to describe is that H1 has a very short attention span, and the actual scientific term is it's sensitive to its environment, which means that it's very light, and the densities are usually very low. So if it's orbiting around in the system that it's in, it doesn't take a lot of gravitational potential over here to make it change its mind and start rotating on the other side. And then you get real-life Gaussian profiles like Mark 279, where the H1 is pretty much in a face-on orientation, so you don't see any of the ears anymore. And I just like showing this one. This one's one of my favorites. This is a pretty well-behaved dual-horn profile, but it looks like it lost a couple of brain cells. And that I can only attribute to That's the physical process that happens to your brain if you choose to watch Batman and Robin. So, what's important about this? Now we know what they look like, where they come from, what science can we get out of using these detections once we have them. The one thing that we can get is H1 mass, or the total mass that's enclosed in the H1 atoms that are giving us this radiation. And that's given by this equation, where it's some constant times the distance in megaparsecs to the galaxy squared, times that integral, which is the total integrated flux of the emission line that we get in our spectrum. So, the next thing we can get is recessional velocity. So let me bring back my George Clooney profile here. Now, like I said, all of the broadening is due to rotation. So if you look at the middle of the profile, you're pretty much seeing the middle of the galaxy. So it is a very good indicator of the systemic velocity of the entire thing. No equations, I just wanted you to know that. The third thing is rotational velocity. Again, all the broadening is due to the rotation of the disk. So if you measure the width of the line, you can get an idea as to how fast the object is actually rotating. There's a couple of ways you can do this. You can take a W50 measurement, which is pretty much just full width at half max. Some people have done W20 in the past, which is the same thing, except taking 50 from the maximum flux, you take it from 20% of the maximum flux. Just depends on how good your signal to noise is and what kind of science you want to do. But that doesn't give you actually how fast it's the maximum rotation, because again, it depends on inclination. So in order to get the maximum rotation rate of the galaxy, you need to know something about its inclination, usually from optical analysis or something like that. And you deproject it down as if it's in a completely edge-on orientation, and that gives you the maximum rotation rate of the galaxy itself. And the most important use of this, the reason why we'd want to know why it's rotating really fast, is other extragalactic applications like distance measurements. So the most well-utilized form of this is the Tully-Fisher relation. And if no one's heard of the Tully-Fisher relation, the basic idea is that galaxies that are bigger are usually brighter, and bigger galaxies like to rotate faster. So there's an intrinsic relation to how fast a galaxy is rotating and how bright it intrinsically is, or its absolute magnitude. And that's what's shown on this plot right here. This is from Cosmic Flows 2 in 2013. And on the x-axis, it shows the log of the maximum deprojected rotational velocity. And on the y-axis is the absolute magnitude in the I band. And then the B, I, and K are all photometric corrections that you need to do in order to make these calculations. And you can see that it's a pretty well-constrained relation. So if you measure the maximum rotation rate, you can get the absolute magnitude of your galaxy. And if you compare that, to the apparent magnitude, you have a constraint on how far away it must be. So there we go. And in case that wasn't enough of what we can get from this line, we can get even more things, which is even more masses. So no matter where you look in space on broad scales, especially if you're looking at galaxies, the most you're going to see is hydrogen. And everything else is going to be not as abundant as compared to how much hydrogen is there. So you can get a constraint as to how much total gas is in this galaxy by using a scale factor that accounts for everything more heavy than hydrogen, which is basically helium. And then everything else, every other gas phase, every other element heavier than that, its contribution is not significant enough to count for more than the typical uncertainty in an H1 mass calculation would be anyway. So the only things that you need to account for are hydrogen and helium, and everything else doesn't matter for these broad calculations. The other thing you can get is baryonic mass, which is the total amount of detectable matter in these galaxies. And the two most significant contributors to mass in galaxies is 1 gas and 2 stars. So if you add those two things up, you get the maximum amount of matter that you can detect in these galaxies. For the ones that I'm looking at, the majority of the AGNs in my sample have derived stellar masses from Benson, Manny, Nicholas 2018. And they also have black hole masses from reverberation mapping experiments, and they're all in the AGN black hole mass database. And if you want to know more about reverberation mapping, you can feel free to talk to me after. But now, the reason why I'm getting all of this is I have a bunch of different masses or a bunch of different properties of these galaxies, and they all represent different parts of the structure or the entire thing. And using the motivation of different scaling relationships that supermassive black holes have with their galaxies, like the black hole to the size of the bulge relation, or the luminosity of the AGN relation, or the black hole to the stellar velocity dispersion relation. We want to probe how many more things about their host galaxies are these black holes connected to. So for example, or for what parts of the galaxies are related to other parts of the galaxies. So for example, you can compare the total mass and gas you have from these galaxies and the total mass and stellar mass that you have for these galaxies. You would assume that if you have a galaxy that has a lot of stars in them, it would have a lower gas reservoir because you used all that gas up to fuel the stellar formation. And that's not always the most direct way to probe that kind of relation. So a more direct way is comparing the gas fraction to the amount of stars that you have, using the same assumption where the higher in stellar mass the galaxy is, the lower amount of gas that you would have because you used all of it up to make all of your stars. So this is a recent result from my paper in prep. We're going to publish it by Christmas. We just don't know which Christmas year it's going to be. So our data is plotted here, and we've plotted a couple of lines that represent different relations to give an idea as to what's going on. The black line is the best fit to our data. The green dashed line is a best fit for gas-rich galaxies that have been quantified by a recent simulation from Stewart 2009, where they used empirical mass relations from a more recent study of nearby galaxies that were very gas-rich and quantified the gas fraction as a function of stellar mass. And you can see that the slope tells you the same thing, where the higher stellar mass you have, the lower gas reservoir you have. But that relation was quantified for very gas-rich galaxies. This sample of active galaxies, the gas fraction is about 6%. So they're very much more stellar-dominated than they are gas-dominated, which is the opposite for the galaxy over here. So that explains why our data lies beneath that one, because there's a lot more gas in the galaxy that they measured. The blue dot dash line is what we call a closed box relation. So there's a one-to-one correlation between the drop in gas and the rise in stellar mass, because you assume that you're putting all of your gas into making stars and that it's not going anywhere else. It's not going in any other formation or any other activity going on in the galaxy. And you can see that the slope is much more steeper than our relation. So something else is going on. The gas is doing just a little bit more than going directly into stellar formation. And the red dot dash line is a constant gas relation. So we're not changing gas mass at all, but we're letting the stellar mass vary for the range of stellar masses that we have. You can see that the slope is almost the same as our best fit relation, and that's because we don't have a very large gas mass range for these galaxies. Turns out that they don't deviate that much. The range is about 10 to the 8.8 to 10 to the 9.4 or 5 solar masses in gas that we have for these galaxies. So a constant gas mass relation isn't very much different than what's actually going on in these galaxies. And then we tried to see if there was any relation or anything interesting happening with the gas fraction as related to the supermassive black hole masses, and it doesn't turn out that they talk to each other that much. So the next thing we wanted to look at is directly comparing gas to the black hole, or baryonic mass to the black hole. And this is again coming from relations of how many properties of the galaxies that the black holes tend to be related to, and using the most recent black hole to stellar mass correlation that was found by Benson, Manuel, and Nicholas 22. But we gas black hole relation, but like I said, we only have 18 galaxies in the sample and not a very large gas mass range. So we need more data to see whether or not there actually is a scaling relation between these two things. But if we look at the baryonic mass black hole mass relation, now we do see a better constraint on the scatter. The thing to keep in mind is that these galaxies already had their stellar masses measured for them in the same vein when they were calibrated for the black hole stellar mass relationship. So that's what mainly is going on here. And like I said, the typical gas fraction was about 6%. But some of them, their gas masses contribute anywhere up to 21% of the total baryonic mass. So we're adding a very significant factor of mass to these galaxies, and we still see a relation. And we wanted to see how this compared to the other end of the spectrum. So what we did was that red cross there represents a derived baryonic mass that we had for what we call the little AGN that could, which is NGC 4395, which is a very low surface brightness galaxy that's still active that has pretty much no bulge. So we expect it to be much more stellar dominated, and it has the lowest reverberation-based black hole mass that we know of. And we got a gas fraction of this galaxy of about 72%, so much, much more gas dominated than it is stellar dominated, and the lowest black hole mass that we have. And we wanted to see where it falls in this relation. You can see it falls pretty close. So this is all evidence to suggest that black holes are not only related to stellar velocity dispersion or the luminosity of the bulge, but it's also related to the total amount of matter in their host galaxies. And that's what I'll leave you with today. I'll leave you with my favorite George Clooney quote, and I'll be happy to take any questions.
So you said you wanted to try to fill in those spots to get a bigger range of the gas
Yes.
masses. Are there like candidate galaxies that have reverberation-mapped masses already that you can observe? Are there like candidates that you know of to fill in that plot, or are they just not?
There's not a direct probe to knowing how much gas is there before we actually get a spectrum for it. And there's a limited sample of galaxies that we can target with reverberation masses because we can only go out to a certain distance in order to see this emission line anyways. So it's kind of a crapshoot. We're observing about 17 more right now, so we're hoping to get a larger range, but we don't know for sure yet.
How does the Milky Way fit? If you compare the Milky Way with your plots?
I haven't thought of that yet, mostly because our galaxy isn't active. So the black hole mass measurement that we have is different than the method used for these galaxies. So it's not a direct comparison, but I don't know of the gas mass or anything about any of the mass of the Milky Way off the top of my head. It'd be interesting to see, but it's not a direct comparison for the things that we're looking at.
Okay. Can you go back like one slide or two? Yeah, that slide. So we have 100 billion stars, right?
Something like that, 1 to 200 billion.
So on the right plot, we would be above the 11.
Somewhere like, yeah,
And our black hole has a mass of 3 times 10 to the 6th.
I believe it.
So it seems like we would be really low compared to your line.
Most likely.
Any comments?
Again, these galaxy scaling relationships tend to have not great constraints on the scatter. And this is still, it's in progress. And again, it's not a direct comparison. For quiescent galaxies, there's different processes going on. For as far as I know, our galaxy is on a diet. The black hole isn't feeding on anything currently.
Isn't the 11 might be an overestimate too?
But anyway, 3 would be off the bottom of the plot.
Yeah, 3 was.
But isn't the Milky Way unusual in our small black hole mass?
I was just wondering, like.
I seem to remember, that it's always been an issue. Why is ours so small compared to